Hi folks, welcome to part 2 of Introduction to Human Biology. As you can probably guess from this image, we're going to talk about homeostasis. First thing I want to say is that the prefix homeo means steady, and the word root stasis means state. So once you build up a bank of prefixes, suffixes, and word roots that are commonly used in biology, it'll make not just breaking down, but learning new vocabulary much simpler. All right, so homeostasis answers the question, how are living bodies regulated? And the technical definition of homeostasis, maintenance of a steady state, is that living things have the ability by changing their functioning, their physiology in real time, to maintain a relatively constant internal environment, even though the external environment is constantly changing around us. One of the reasons I like this particular image of an acrobat who's balanced on little can here is that it says a lot about what homeostasis actually is, right? Homeostasis requires a lot of energy, and for that we require fuel, which we'll talk about next week. The other point to take away from this image, not only does it require a lot of energy and a lot of skill, in the case of homeostasis, biochemical skill, but you can also imagine, and this guy is a circus performer, he's actually pretty far up in the air, balanced here. So if he loses his balance, and this is not balance with the external environment, right? It is balance within his internal environment. He's going to get hurt. And that's also the case with failure of homeostasis in our bodies. Changes that are when parts of our physiology change far outside the normal limits, that's when you have illness and potentially death. So the two systems in the body that are, you can think of it in a way as being sort of in charge of homeostasis, are the nervous system, which is here, and the endocrine systems, which are slightly different in males and females because we have different gonads. Women have ovaries, males have testes. Both of these systems send or use chemical messengers to affect the functioning of other systems. The nervous system does that with direct physical connections in the form of nerves from the brain and the spinal cord that carry electrical signals that get converted into a chemical message and then cause an effect. The endocrine system releases its chemical messengers, its molecular messengers, into the bloodstream, and so they travel throughout the body. So some vocabulary that's important for homeostasis. The first is set point. Set point refers to sort of the point where the system is balanced. So if we think about blood pressure, for example, which is governed by homeostasis. The set point for someone with normal blood pressure is, say, 110 over 70, 120 over 70, something like that. Right, when blood pressure gets high, because let's say you've been running, right, that's a stimulus. That the running is a stimulus that causes blood pressure to increase, so that takes you above the set point. That's detected by some feature of a homeostatic mechanism. Sometimes these are called sensors or detectors or receptors. The point is that the environment is being monitored for changes in what we refer to as a variable. And variable just means something that can vary, that can, right, your blood pressure can be low, it can be high, it can be around the set point. The information from the detector or sensor is sent to a control center. And the control center has a fairly complex job to do. It knows, quote unquote, knows what the set point is, and it compares information coming in from the sensor to the set point, which is what we mean by interpreting input. And then by making that comparison, generates a decision about if some aspect of your body needs to change in order to bring the system back to the set point or close to the set point. So if the control center decides that something needs to be done, then a signal is going to be sent through the effector. So the effector is what is going to cause a change in the variable. So let's say, again, if we use the example of blood pressure, there are sensors, which would be part of what we refer to as the afferent pathway, the pathway that's carrying information to the control center. The efferent pathway includes the effector, what's going to effect a change, as well as whatever is carrying the signal. So if we're talking about blood pressure, the afferent sensor would be pressure receptors in a part of in different parts of the brain, as well as in certain arteries in the body. The control center for blood pressure would be in the brain, and the efferent pathway involves a number of different potential structures. So if your blood pressure goes up, and that's the stimulus, or the stimulus causes your blood pressure to go up, it's detected by the afferent pathway, the sensor. And then the control center decides that, hey, that's a little too high, we need to bring it down. The efferent pathway will send a signal out to, let's say, smooth muscle associated with with small arteries, and say, hey, folks, relax. I want you to quit contracting. So that increases the size of the blood vessel, and that in turn generates the response, which is opening the blood vessels a little bit more widely, and that leads to a change, a decrease in blood pressure. Now, there are two major mechanisms for maintaining homeostasis. Actually, there's one major mechanism. The other is used just in special cases. So negative feedback is the major mechanism. And if you think about it for a second, I think you'll see why. So when we say feedback, essentially means that information is flowing through some sort of biological system, and that the information flow, the action that's taken, is linked back to the initial stimulus. The negative in negative feedback doesn't mean decrease. That's a really important point. So it's not like math, even though we use plus and minus signs sometimes. Negative feedback means that whatever the body's response is, it counteracts the original stimulus. And right, so think about the guy balanced on the tube, the acrobat balanced on the tube. Somebody pushes on one side, he's going to have to lean to the other. He's going to have to go in the opposite direction to stay at a steady state. So if your body temperature rises, right, so it's going up, which is why I put a plus here, getting warmer, that leads to a response such as sweating, which decreases body temperature. So the response counteracts the stimulus. Positive feedback, well, let me back up for a sec. So also with negative feedback, right? Let's say your body temperature falls, right? So we might use a minus sign for that. Well, with negative feedback, the response is going to be something that, like shivering, for example, that leads to an increase in body temperature. So again, it's not that the change is always negative or in a negative direction or a positive direction. It's that the change is always opposite to the stimulus. Right? And it makes sense. That's got to be the major mechanism for maintaining a steady state. Because, again, think about our friend the acrobat. If somebody keeps adding weight to one side and that of his little balance board, and he keeps adding weight by leaning to that side, he's going to fall off, right? There's no return to homeostasis. Whereas if he leans in the opposite direction, he adds weight to the opposite direction with his body, he's going to stay balanced. Positive feedback is much more rare in a healthy body. And it's easy to see why that would be the case as well. So when we say positive, right, we don't mean always a change in a positive direction. What we mean is that the response reinforces the original stimulus. So it's in the same direction, which is why I've got pluses here. Another way of describing this is to say that positive feedback is self-amplifying. So one of the examples of a healthy positive feedback mechanism involves breastfeeding. So a baby suckles at a woman's breast, and through a complex chain of events, that stimulation of the breast leads to milk ejection. Well, when the milk is ejected, that makes the baby suckle harder, which makes more milk be ejected. And it's a self-amplifying cycle. Now, the reason why this is not a pathological or a disease-causing positive feedback mechanism is that eventually the response leads to removal of the stimulus. Eventually, right? So eventually the baby's full. And the baby stops suckling, and that interrupts the positive feedback loop. Okay, so you can kind of see, I'm trying to make it really clear that this is super important to remember. Negative feedback's the primary mechanism for homeostasis. Stimulus, you've got the response, and we've got all of the different elements in what we might call a homeostatic mechanism, some sort of sensor, a control center, an effector. The important point is that the response counteracts the original stimulus. A couple examples that we'll be talking about in this course. Maintenance of stable body temperature, the acidity or alkalinity of the blood, the level of blood glucose, blood pressure. Pretty much everything you can think of is in a healthy body that's trying to think of examples other than blood clotting where you have positive feedback. I can't. All right, so here's negative feedback, right? So the stimulus is a decrease in body temperature on the left side or an increase on the right side. And, sometimes students get caught up in, well, okay, is the stimulus the decrease in body temperature, or is it the change in the environment? Either one, you can make an argument for either one, and I'm okay with you making those arguments. So we could say a decrease or an increase from set point. I have to order a new pencil. I think my pencil's too fat. Or you could say it's a decrease or an increase in temperature around the body, right? The sensors are temperature receptors, which are in the skin, as well as other places in the body. The control center in this homeostatic mechanism is in the brain. The effector, and so I'm just going to talk about if you get cold, right? And you guys can sort of think through the process for how this works if you're too warm yourselves. So the effector, there can be a lot of different effectors. So you've got shivering as a response, and that's due to your skeletal muscles quivering. So, right, you might get goosebumps if you're cold. Those goosebumps are the result of your hair standing on end. Whoops. Yes, I'm just having trouble this afternoon. Okay. All right, and what that does is trap a layer of warm air next to the body. So there can be, and often is, more than one effector, and a whole suite of responses that lead to a return to homeostasis, to the set point. So another helpful way of displaying negative feedback, or regulation by negative feedback, is with a graph. So we've got, let's see, how can I do this? We have what's referred to as the y-axis here. And on that axis, we're going to plot a change in our variable. So still go with, we'll go with temperature. So change in internal body temperature. And then on what's referred to as the x-axis, I have temperature, time. So y-axis and x-axis. So I've plotted the set point. So for body temperature, right, we would roughly 98.6. And our body temperature varies over the course of the day, as well as in response to changes in the environment around us. It goes down, and it goes down, it goes back up. So you have these, homeostasis doesn't mean no change. It means that the system, in this case, body temperature, is maintained within a relatively narrow range that's compatible with life. So let's think about what happens if you get really hot. Let's see, yellow there. Let's see, you get really hot. Not only does that feel pretty crappy, it's also your body's attempt, usually, to rid you of some sort of an infectious microbe. Your body temperature can end up getting so high that it kills you. And that's because it has a lot to do with these macromolecules called proteins that we're going to talk a lot more about next week. You can only heat them so much before their shape changes forever. And once that happens, they don't go back to the normal shape. If you get super cold, right, that can also lead to death. And that has to do with the fact that our metabolism, all of those chemical reactions inside our body, they function best at more or less 98.6 degrees Fahrenheit. Temperature is a measurement of how fast molecules are moving, and if they slow down too much, then the chemistry of life doesn't work. Okay, so positive feedback leads to a change in the same direction, right? And there are, right, so you've got the stimulus, and whatever the response is intensifies, it amplifies the original stimulus. And the three examples that I can think of where you have positive feedback in a healthy body are childbirth, blood clotting, and the milk letdown reflex, which is the example I used just a little while ago. So here's the example of labor and delivery. I've got a question mark here because, as far as I know, we still don't quite understand exactly what triggers the beginning of the birth process. We have a good idea in sheep, but, sheep and people, a little different. There's a lot of same mechanisms, but in any case. All right, so once that process begins, right, what happens is the baby's head moves down and engages with a part of the female reproductive system that sits between the uterus and the vagina. It's a narrowing called the cervix. Within the cervix, there are stretch receptors, right? So pressure from the baby would be the stimulus. Stretch receptors in the cervix are part of the afferent pathway. Those are the receptors. And that information is carried by nerves into the brain. The brain tells a part of the endocrine system to release a hormone called oxytocin, right? Pitocin is the artificial form of oxytocin. When oxytocin is released, it's released by an endocrine gland into the bloodstream, travels through the bloodstream to the uterus, where there are receptors in the smooth muscle of the uterus, and it causes uterine contractions. Well, when the uterus contracts, forces the baby's head down farther into the cervix, and that leads to increased stretching, and it goes on until out pops the baby. So the oxytocin hormone, the gland that releases it, are both part of the efferent pathway. The effector is the uterine muscle. Okay, so this slide is just a quick summary. I'll let you guys read through that. So thought question, right? Here's the graph again with the variable that's being measured on the y-axis. So you've got high and low. Got the set point marked here. The green line represents what you would see with a negative feedback mechanism. So what would you add to this diagram for a positive feedback mechanism? Just think to yourself for a second. So, right, the more actively you engage with the material, the better. So try to imagine what kind of line you would draw. Okay. So if I want to show on a graph, remember with negative feedback, we've got change in the opposite direction, right? Positive feedback, you have change in the same direction. I'll use light blue for this. So if, right, I've got my set point, if it was a positive feedback mechanism, right, and it's, right, usually positive feedback and loss of negative feedback are involved in a lot of disease processes. So if we have a disease process where we've got positive feedback happening, right, you've got an increase, which leads to an increase, which leads to an increase, which leads to an increase. No return to the set point. You have a decrease, a decrease, a decrease, a decrease, a decrease. No return to the set point. So what we need to see for a positive feedback mechanism to work in a healthy body is that the result of the positive feedback mechanism is eventual removal of the stimulus. So take a look at this question, think about it, and we will talk about it in our Collaborate next week. Make sure you pay attention to that.